Welcome to UVU CS3060 Lecture 5.4, where we discuss the round-robin scheduler. So, the two schedulers we've discussed so far have had their own particular issues. We watched the first-come, first-serve cause issues with short burst processes when a long process was at the top of the queue and couldn't be interrupted. We called this the convoy effect. And we saw problems with the shortest job first and shortest remaining time first schedulers when there were too many very short jobs on the system, that it would cause the long jobs to not be scheduled CPU time and starve them of CPU time. Starvation is a big problem with most priority-based queues, which shortest job first and shortest remaining time first are. So now we introduce the round-robin scheduler. Now before we start, we need to be aware that round-robin is by its very design preemptive. So what happens with the round-robin scheduler is there is an amount of time that is decided upon for all processes called a time quantum. This time quantum, it gives a length of time that a process can run before it is interrupted, and it is interrupted by a timer. This is a special piece of hardware that the CPU has to have implemented for round robin to work. Without the CPU timer, this does not work. The round robin doesn't work. So once the time has elapsed, the process is stopped or preempted, and it is added to the end of the ready queue. So it acts very much like a first-come, first-serve scheduler. Jobs come off the top of the queue, and they are put to the bottom of the queue whenever they're ready to be on the CPU. The only difference between round robin and first come first serve is that round robin is preemptive. In other words, it preempts the process before the process is finished. Now, consider a ready queue that has n processes, and that we have a time quantum at Q. So with those n processes, each process will get 1/n of the CPU time in chunks of Q time units. So it's cycled through. If you have 5 jobs, those 5 jobs will be run. Each job will get 1/5. It will be allowed 1/5 of the CPU time in Q time units. Now, with that in mind, no process waits more than n-1 times Q time units. So if I have 15 jobs on the queue, and the job at the bottom is going to needs to know how quickly it's going to run, it will run 14 times, let's say time quantum of 10, 14 times 10 time units. And so in that particular case, if we have 14 other jobs times 10 milliseconds, that particular job at the bottom will wait no more than 140 milliseconds. That means that the convoy effect is effectually done away with. Now, mind you, there's a lot of jobs here. Let's consider the first come, first serve we saw before. There were 3 jobs. If we have 10 milliseconds, if there are 3 jobs in the queue, then none of these are going to wait more than 2 times 10 milliseconds, 2 jobs times 10 milliseconds, or 20 milliseconds. Now, this may still seem like a long time, but let's remember here that this is a maximum, that it will be less than or equal to the wait time So 20 milliseconds is an upper bound. So 20 milliseconds will set how long a job will wait. That is certainly a lot shorter than the 27 milliseconds the last job was experiencing. Now, again, like I said, the timer interrupt is what makes the quantum work here. Now, when it comes to performance, how do you choose a quantum that is fair but is still efficient? Well, if we set the queue too large, then what this becomes is the first in, first out queue. If you consider our 24, 3, and 3 job, if our time quantum, if our job list, if job 1 is 24, job 2 is 3, and job 3 is 3, if our time quantum is 25, then this job 1, is clearly going to run to completion, which means we still experience the convoy effect, and this really is going to act just like first in, first out. We'll never hit the timer interrupt. If it's too small, especially when it comes to the respect of the context switch, well then, if let's say we have a context switch that is 3, but our quantum is 2, but our context switch is 3, well then it looks a little bit like this. We have our context switch, and then we have just this blip of a job, and then we have our context switch, and then we have this little blip of a job. In this particular case, all of these context switches add up, and we end up running more. The OS kernel runs more time than the actual user jobs on the system. And we don't want this. This is not an efficient operating system when the operating system is running more than the actual user jobs. So we want to find a balance between too large of a time quantum and too small of a time quantum for a round-robin system. So here is that example again. Let's take a look at how this system works with a time quantum of 4 with those 3 jobs that we saw before. Now in this particular case, we start out at time 0 running the process at the top of the queue. And in this case, the process at the top of the queue is process 1. It's going to CPU burst for 24 milliseconds. Well, that's fine. It can go ahead and do that, but the timer is going to stop it after 4 milliseconds. So whenever time becomes 4, the queue changes around. We end up with process 2 on the top, process 3 next, and process 1 is pushed to the bottom. Now process 2 has a burst of 3, process 3 has a burst of 3, but process 1 now has a burst of 20. So we're going to keep track of how long this burst is for our simulator. So the question now is, which comes first, the time quantum or the end of process 2? Well, clearly the end of process 2 comes first, and so our next event is going to be at T7, at which point we have process 3 on the queue, process 1, and now process 2 has been eliminated. It's no longer going to be put down to the bottom of the queue because its burst time is 0. Process 3 has 3 milliseconds left in its burst time, and process 1 still has 20 left in its burst time. So what's the next event? A time quantum or process exit? Well, in this case, process 3 will exit before the time quantum of 4. So the next event is at time 10. At which point, process 3 is run to completion, and process 1 ends up at the top of the queue for 20 milliseconds. So what's the next event after this? Well, the next event is clearly not the end of the process, because it's going to run much longer than our time quantum. So we go to time 14, which puts this process back to the bottom of the queue, which in our case is at the top, and it has run 16. So what ends up happening is time 0 we start, time 4 is the first event, time 7 is the second event, time 3 is at 10 milliseconds, and then we start interrupting process 1. So process 1 runs to 14 milliseconds, then it runs to 18 milliseconds, and then it runs to 22 milliseconds, then it runs to 26 milliseconds, and then finally it terminates at 30 milliseconds. It runs out because at the end of this time quantum, it has 20 milliseconds left in burst. At the end of this, it has 16. At the end of this, it has 12. At the end of this particular quantum, it has 8. At the end of this quantum, it has 4. And at the end of this quantum, it has 0, and the process terminates. So this actually has a higher average turnaround time, just simply because in the shortest job first, process 2 and process 3 would have been taken care of first, and its turnaround time would have been excellent. And then process 1 would have, of course, taken the time it's going to. But the response time of this is significantly better, because in shortest job first, because process 2 and process 3 would have been started first, it would have been 6 milliseconds before process 1 got to start, which is not a very good response time. But in this particular case, every process gets a response time that's reasonable. So again, quantum should be large compared to the context switch time. We have not calculated context switch time in here at all. All we're doing, and context switch time would happen every time we have an event. So perhaps this is something that's important to do for a scheduler, and it will be extra credit for this particular assignment. Now, the time quantum is usually 10 to 100 milliseconds, as long as context switches are less than 10 microseconds. And this is fairly common in operating systems. Operating systems work very hard to make context switches very fast. So you can see here, we've got different time quantums for a process time of 10. So with a time quantum of 12, that particular event runs it to completion, and thus it never hits its time quantum. There is no technically times or context switches in this particular setup. If we set the time quantum to half, to 6, we get 1 context switch. But if we have the time quantum set to 1, we can see that there's a context switch every single cycle here. And if each of these each of these context switches, let's say, takes 1 millisecond, we're going to go large here. Well, the total runtime of this particular of the time quantum of 12 is just 10 milliseconds. With the time quantum of 6, it's 11. So it's 1 plus the length of the process. And here, because we have 9 context switches, this 10 millisecond job with 1 millisecond context switches becomes a 19 millisecond job. Takes forever to finish it in the context of that particular process. We don't want to set a low time quantum. We want to find something in the middle. And you can see that average turnaround time generally is affected by the length of the time quantum. And so whenever with a process list such as this, such as what we have here, we can see that the average turnaround times actually vary quite widely depending on what the time quantum is. With a time quantum of 5 here, we can see that it actually has its largest turnaround time as opposed to a time quantum of 3. So it's a good idea to adjust this or have a value that works for the particular system. Now, it doesn't show it in this diagram, but it is suggested that 80% of all CPU bursts should be shorter than the time quantum, meaning that they don't get interrupted. But there will be some long CPU bursts, and those should be interrupted after a time quantum of Q. This ends UVU CS3060 Lecture 5.4, where we discuss the round-robin scheduler.